In this video, we're going to talk about the surface area of parametric surfaces. So let's define what a parametric surface is. It's a surface described by two parameters, u and v, and we'll do an example here so that we can visualize this. So when we're talking about parametric surfaces, we usually define it in terms of what's called a position vector. So we write vector r of uv, and this just represents the different positions or different points, you could say, on the surface. And then we'd have a formula, vector with three components, that defines all our different points on this surface. So for this example, let's say it looks like u cos v, u sine v, and then u squared. And we'd have some range of values given as part of the definition of the parametric surface. So let's say for this example, u ranges from 0 to 3, and v ranges from 0 to 2 pi. So in order to understand this particular parametric surface, let's try graphing it. So we're in 3D, and our surface is a two-dimensional collection of points. So let's see if we can start plotting some of these. The way I might approach this is I would think first about what happens when u equals 0. So if we just plug u equals 0 in here, we get 0, 0, 0. Meaning we're just getting the origin. Okay, I'm going to put some scale on the z-axis here. I think for the purpose of this graph, we'll go up to about 9 units. So we'll see if we can get all that on there. Okay, so I'm going to identify z equal 1, 4, and 9 because I think those are going to be important values for the sake of this sketch. And let's now think about what happens when u equals 1. Okay, so when u equals 1, the z coordinate is 1, and the x and y coordinates are cos v, sine v, where v is somewhere between 0 and 2 pi. So we're at the z level 1 here, and what's happening in the xy plane, or in the xy direction, we've got a circle of radius 1. That's what cos v, sine v defines. As v goes from 0 to 2 pi. So let's imagine at the z level 1 just drawing a circle of radius 1. Okay, so all those points are on our surface, and so is the origin. So same thing at u equal 2, our z value would be 4. So we're up here. And what's happening in the x and y directions, we've got x values like 2 cos v, and we've got y values like 2 sine v. So as v ranges from 0 to 2 pi, that's going to trace out a circle of radius 2. Okay, so let's add a bit more scale in the x direction. I think we're going to want to go about 3 units out, same for y direction. So at the z level 4, we've got a circle of radius 2. So let's say it looks like that. And then let's do finally u equal 3. I think that will give us enough info to finish the sketch. So at u equal 3, we are at a z value of 9. And our x and y values look like 3 cos v and 3 sine v, as v ranges from 0 to 2 pi. So v is our angle that's representing us rotating around here. We're getting a circle of radius 3. So let's try it like that at the z level 9. Okay, so if you imagine filling in the details, you could think about all the real numbers between 0 and 3. At each level, we're getting a circle of a certain radius. And if you were to put infinitely many of these circles on here, it'd be getting wider as we go up, then what you're building is this surface here. So this is actually just another way of representing our familiar paraboloid z equal x squared plus y squared. So in a parametric surface, instead of having your surface defined in terms of x and y, you've got your surface defined in terms of two other variables called parameters. Typically they're called u and v, but you could call them a and b, and the values would be defined as part of the definition of your surface. Okay, so that's what a parametric surface looks like. Now let's see the formula for surface area for a parametric surface. So our formula will somehow have to involve these parameters u and v, and this is specifically how it works. So surface area is going to be the double integral over r of the length of r sub u cross r sub v du dv. But let's look in a little bit more detail at this integrand. So when we write something like r sub u, that means take the partial derivative with respect to u of this position vector. So just go through component by component, take your partial derivatives. So that gives you a vector. And then in the same way, you can calculate your partial of r with respect to v. So that gives you another vector. You're taking the cross product of those. So that gives you another vector in 3D. And then you take the length of that. And that gives you an integrand that can be integrated over your region R. So that's how we're going to find surface area of a parametric surface. And let's try an example. So let's find the surface area of the following parametric surface. This vector R, remember from our previous discussion, is called the position vector. So it's just describing the different points that come up on our surface. And the points look like a cos b, a sine b, a, where a is ranging from 0 to 2 and b is ranging from 0 to 2 pi. Now, we don't, strictly speaking, need to have a graph in order to solve the problem, but I'm going to do the sketch just for the sake of getting a bit more practice with parametric surfaces. Okay, so what we're drawing here, x, y, z axes. And the way we're going to define some points is maybe let's just look at a values 0, 1, and 2, and we'll figure out what points correspond to each of those a values. So when a is 0, if we plug into our position vector, we just have 0, 0, 0. Okay, so the origin is on our surface. If we sub in a equal 1, then we're getting a z value of 1, and our x value and y values look like cos b, sine b, where b is going from 0 to 2 pi. Okay, so whenever you see cos b, comma sine b, that's just a parametrization of a unit circle. So meaning at the z level 1, what's happening in the xy direction is that we're getting a unit circle. So there we go. And then let's talk about what's happening when a equals 2. So when a equal 2, we feed that into our z coordinate. Z is 2. And if we feed that into our x and y coordinate, we get 2 cos b and 2 sine b. Okay, so 2 cos b comma 2 sine b, that describes a unit circle, or sorry, a circle of radius 2 rather. So let's add a bit more scale in our x and y direction. There we go. So at a z level of 2, circle of radius 2. Okay, and then you could imagine talking about all real numbers here between 0 and 2. So for any given z level, you're getting a circle of that specific radius centered at the origin. So if we were to actually fill in all the details here and complete our surface, what we would see, straight sides, if we draw our picture perfectly. So this is actually a cone. Vertex at the origin, opening upwards, and then it gets cut off at the z level, z equal 2. So when we talk about this cone, the surface is just the outer shell, just the side of the cone that's being captured here, and we're trying to find the surface area. So if you imagine that cone being formed out of a piece of fabric, and then imagine just pulling this fabric flat, how much area would be taken up by the side of that cone? Well, in this problem, our parameters are called a and b rather than u and v. But what we're supposed to do is calculate the two partial derivatives of our position vector. So let's find r sub a and r sub b. For r sub a, it just means go through your vector, take partial derivatives of each component with respect to a. So you'd have cos b, sine b, and 1. And if you do the same thing for b, minus a sine b, a cos b, and 0. So next what we need to do is take the cross product of these guys. So r sub a cross r sub b. All right, so let's set up a 3 by 3 determinant here for our cross product. We'll put vectors I, j, k at the top, put our first vector into the second row, and put our second vector in below that. And then we're just going to calculate this 3 by 3 determinant. So let's do cofactor expansion along the top row here. So we're going to have I times this little 2 by 2 determinant. So that's going to be minus a cos b. Remember with cofactor expansion, you've got alternating pattern for the signs. So you've got that sort of sign pattern there. Signs alternate as you go right or down. So we're going to have minus j times, cross out that row and column that the j is in, and let's look at our 2 by 2 determinant. It would be a sine b. And then finally plus k times, we'll do this little 2 by 2 determinant there. Okay, so we might need a little bit more room to write. I think I'll do the last term on the next line so we can show all our steps here. So we're going to go plus vector k times that 2 by 2 determinant is going to be a cos squared b, and then plus a sine squared b. Okay, and if we were to actually factor out the a here, you'd have a times cos squared b plus sine squared b, which would be 1. So in other words, this whole thing is just becoming a. Okay, if we write this vector into our component notation, we'd have minus a cos b, minus a sine b, and then a. So our goal now is to calculate the length of this vector, and that's going to be our integrand for computing our surface area. So length, we're going to take the square root and we're going to go through and square each of our components. So we'd have a squared cos squared b plus a squared sine squared b plus a squared. And let's see if we can do some simplifying here. So for the first two terms, you could factor out the a squared and you'd have cos squared b plus sine squared b, and then you'd still have your a squared at the back. So for those first two terms, the cos squared b plus sine squared b is going to give us 1. In other words, under the root, we've got just an a squared plus a squared, so 2a squared. And we can then pass the square root to each of those factors. We can say that's root 2 times a. Now we have to be a little careful here. When you take square root of a squared, technically what you're getting is the absolute value of a. But if you remember from our definition in this problem, we said that a was ranging between 0 and 2. So because we know that a is positive, or at least not negative, we don't need those absolute value signs there. So it is safe to write root 2a, but in general, you have to be a little careful about that. Good, so now we're ready to actually compute our surface area. So in general, surface area for parametric surface, going to be the double integral over our region of the length of r sub a crossed with r sub b, and then dA. So let's fill in all the details here. In this context, dA just represents du. Well, in general, you'd say du dv, but in this case, our parameters are a and b. So you could write dA db, or you could do this in the other order, db dA, it doesn't matter. So we'll just pick one, we'll say dA db, and then that will define in what order we put our limits of integration on here. So our integrand is root 2a from our calculation above. We're going to do dA db, and then we'll just fill in our limits of integration based on what we were told in the problem. So a was ranging between 0 and 2, and b was ranging between 0 and 2 pi. So I think we're good to go here. Integrating with respect to a on the inside, we'll just leave the outer integral and the outer dB on there, and let's do our integration for a. So we'd have root 2 a squared over 2, and that's going to get evaluated at a equal 2 and then a equals 0. Okay, so we've got integral from 0 to 2 pi dB at the back. Subbing in a equal 2, we got the root 2 times 4 over 2. So let's call that 2 root 2, and then evaluating at a equals 0 would give us 0. Okay, so in other words, we've got this constant 2 root 2, and then we're just going to integrate from 0 to 2 pi dB, and that's going to give us 2 pi. So overall, here's our final answer coming up. 4 root 2 pi is the surface area of that cone. So that gave us a bit more practice with a couple of different things. One, we got a bit more practice with just graphing a parametric surface so that we're comfortable with that, and using the position vector to figure out which points are actually on that surface so that we can get a visual. And then we actually went through the process of using the partial derivatives of that position vector to come up with our surface area. Thanks for watching.